Okay, well, hopefully you made sense of the question. But let's just take the first force we calculated, the 0.09 newtons times I on the 5 microcoulomb charge at the 0.1 meter zero position, right? Well, what's the force per unit charge? Well, it's 0.09 newtons times I on a 5 microcoulomb charge, so the force per unit charge is 0.09 newtons times I divided by 5 microcoulombs, right? And what's that? Well, 9 divided by 5 is 1.8, right? It's like we've got 0.018, but then we're dividing by 10 to the negative sixth, right? Which is going to give us another 10 to the sixth. So that's going to be, well, let's see, 0.018 times a million, right? I believe that's 18,000. Newtons per coulomb times I. Okay? And that equals never mind. Yeah. I almost did something stupid. Okay. Got it? So all we have to do is divide each of these forces by 5 microcoulombs, and we get the force per unit coulomb, right? Per unit of charge. Now I'm going to draw a little map with the results of this, but you should work these out. Very simple. Okay, so at this point, I'm saying we have...
Mr. Smith, I got a question.
Yeah.
Why is it 5 instead of 2 if 5 is the charge at the origin and 2 is the one at each individual point along the axis?
I thought the 2 was at the origin.
Oh, okay.
Okay, well,
I mean, that's not a big deal. It's an easy fix. I was just wondering.
that's good. I got them backwards.
No, that's
Sorry.
okay.
Okay. So, yeah, that was backwards, but I'm going to change it on the document so nobody can prove that I made a mistake, and I'll just say that you forged these papers that you have in your. I admit my error, and I'm not the least bit surprised. Now, I mean, of course, I'm not surprised to admit it. Okay, well, okay, so here we have the 0.01 meter or 0.1 meter position, right? So now I can say I've got a vector here that represents the force per unit of charge, right? Okay. Now, I come out here, and what's my force per unit of charge going to be at the 1 meter position? Well, what happened to the force if I went from 0.1 meter to 1 meter?
It decreased.
By what factor? I'm 10 times as far.
Yeah.
Yeah.
It's 0.9.
It was by 100, right?
Yeah, by a factor of 100,
Yeah.
because it's an inverse square, and we need to get used to that with these numbers, right?
Yeah.
Okay? It's an inverse square force, so it's going to be 100 times weaker, so it's going to be out here, it's going to be 180 newtons per coulomb times I, which is so short I can't even draw it. Just a little tiny vector, right? 100th as long as this one. Okay? Now, as you go from here to here, you could integrate this from here to here, which would give you what?
Work.
By
get work. Work what? Work per unit charge, right? Which would be your 8.1 times 10 to the negative third joules divided by 5 microcoulombs equals, right up there, 1.602, no, 1.62 times 10 to the negative third it's not negative third, you have negative third, but that's got a negative 6 on it. And the 5 gives you actually, yeah, it's still the same order of magnitude, but it's going to be times 10 to the plus third, because you're dividing by 10 to the negative 6, right?
Yeah.
Okay? And that's joules per coulomb, right? Equals 1.62 times 10 to the third. What do you think a joule per coulomb is? Have you ever, you'll recognize this term, but now you know what it means in a minute.
Oh, it's
That's what a volt means. No, don't say what. That'd be the rate at which you do the work. Okay. Got to be careful when you say that in a physics class, right? You got to make it really clear. What? Not what. I don't know what you say because I can't hear that well. Okay. 1.62 times 10 to the third volts. Now, big definition. Potential difference from 0.1 meter to 1 meter due to 2 microcoulomb charge at the origin is what?
They do the battery together.
You did.
90 cents two for the
Delta PE per unit of traveling charge. Negative. .62 times 10 to the third volts, negative 1620 volts. Okay?
Is there abbreviation?